The Vercors district of southeast France is a spectacular plateau area rimmed by these cliffs of Cretaceous limestones. It's a spectacular landscape and it's a great place to do structural geology. We're going to look at the role of inherited structures and inherited stratigraphy in controlling the alpine structure that we see today. And then we're going to explore the use of displacement patterns in 3 dimensions to test competing interpretations of subsurface structure. So, we're in the Western Alps, and in this region the thrust belts are made up of stacked Mesozoic strata. As we've seen from that view, they're dominated by platform carbonates. This part of the thrust belt was emergent, so the thrust broke up to the Earth's surface without being buried by other thrust sheets. The deformation is Miocene in age and it's detached from the underlying crystalline basement. And we're going to look at the role of inherited structures and the formation of the Vercors Plateau. And then we're going to test competing interpretations of the subsurface by looking at displacement patterns. This is the map of the French subalpine chains and Jura. We're in the southern part of this, the Vercors there. On this map, the Cretaceous and Jurassic rocks are coloured up green and blue respectively, and they're overlain by tertiary molasse sandstones that are deformed as well with the structures. So let's look at a detailed map of this Vercors district and its stratigraphy. So the detailed map shows the Vercors Plateau there, which at outcrop is dominated by the Ergonian limestone, shown here in the sort of tan orange colour. The plateau is bordered on its eastern margin by the deep cut Drac Valley, within which the underlying Jurassic sediments are exposed, and the Vercors Plateau is bound to its western margin by the fallen basin that contains the Miocene, with a little re-entrant called the Royan district. So the stratigraphy across here changes dramatically. The Miocene fallen basin deposits are underlain by a platform-dominated Jurassic and mid-Cretaceous succession. But this expands dramatically until we get to the Drac Valley, where the section is many kilometres thick and the platform carbonates are separated by important incompetent shale units. So there's a dramatic change in stratigraphic thickness and facies as we go from west to east across this map area. And it's the Ergonian limestone that dominates the landscape. And its spectacular cliffs form the eastern rim of the Vercors Plateau. Let's look at this on a digital elevation model. There's the eastern rim, and the high ground is shown by brown colours on here, which look rather like a rucked up tablecloth, and that's largely made up, at outcrop, of the Ergonian limestone. And the whole rucked up tablecloth then dives under the Royan area and under the fallen basin on the left hand side. Okay, so let's see what this landscape looks like. And here we are, looking northeast across a landscape of Ergonian limestone. And there in the distance is a line of hills that lie along the eastern rim of the plateau. Well, the plateau dives off to the west. And here it is, you can see the Ergonian cliffliner here, piling off and going underneath the foreland area that off towards the northwest. So a couple of shots there of the landscapes of the Vercors district. You can get some insight into the structure from these deep cut gorges on the margins. So that last view was looking in the direction of the red arrow on the map. So let's now look at a cross section through the region. We can use the stratigraphic thicknesses that we can see in wells out in the foreland and at outcrop within the plateau in those deep cut gorges and from the eastern end above the Drac Valley. So here's the cross section running through here, and here it is. So west-northwest on the left, east-southeast on the right, the section is drawn more or less parallel to the direction of thrusting. The Ergonian limestone is that orange unit at the top of the cross section that dominates the outcrop of the Vercors Plateau, and you can see as you pass across Royan into the Basse Dauphiné area that the limestones dive underneath the molasse, the yellow rocks, which are the tertiary sandstones. So let's start off looking at the thrust front. And the thrust front is shown in this interpretation to be located by an early normal fault. And that normal fault we can infer from the change in thickness of the stratigraphy as encountered in the well that underlies the Basse-Dauphiné basin compared to that we find at outcrop, just a few kilometres to the east. So in the well, the Jurassic and lower Cretaceous rocks are very thin, rather less than a kilometre, but as we go into the first anticline in there, the section greatly expands. The rapidity of that stratigraphic expansion implies the presence of a fault, the faille de l'Isère, the Isère fault, which downthrows originally towards the east-southeast, which has allowed the accumulation of thicker Jurassic and lower Cretaceous strata. So this fault appears to have located the thrust front. The frontal anticline has been carried by a thrust ramp that has peeled off its basal detachment at the faille de l'Isère. But what about the plateau itself? Why is the plateau so high? What's its structure? Well, there are a few thrusts that cut the plateau. Here's one of them. It's the Vercors thrust. We're looking back into the thrust direction in here. The cliffs are the Argonian limestone. The grassy areas that lie below, just along that road section there, are Miocene sandstones. So there's the thrust, and we can see bedding in the Argonian limestone coming down against the thrust plane, creating a hanging wall ramp geometry. So a fairly dramatic thrust structure. And that's where we saw it in that gorge section that we can see picked out in the digital elevation model. But this thrust rapidly loses displacement as we go south. On the line of cross-section, the thrust has almost disappeared. It's this little structure here. So, although there are thrusts that cut the Argonian sheet that defines the plateau, they're rather minor. They're certainly not enough to account for its elevation. So why is there a plateau of Argonian limestone? Why is it so elevated relative to its position beneath the Basse-Dauphiné? Well, we can begin to get an idea by looking at the restored section below. This restoration has been hung from the Argonian limestone, which is assumed to have been more or less horizontal initially. It's cut by a few faults you can see in the middle beneath the scale bar, which are Oligocene in age, which are associated with the adjacent Rhone-Graben system. And we're not too worried about these. And it's worth pointing out here that they don't appear to be reactivated by thrusting. The thrust structures seem to cut straight across them. Okay, so returning to the Argonian, if we put that horizontally, we can use that as a datum from which we can hang the underlying stratigraphy, so measuring the stratigraphic thicknesses from the cross-section and reporting them back on the restoration below, we can build that restoration and define a stratigraphic template that increases in thickness from west to east. And this is consistent with our observations from the Basse-Dauphiné, where the stratigraphy is thin, in other words in the west, and the greatly expanded succession that we see exposed on the hillsides of the Drac Valley, over there in the east. So the thrust system, if it detaches from basement in here, the basal thrust must climb gradually up that inclined basement surface from the east-southeast to the west-northwest, carrying with it in its hanging wall a wedge-shaped stratigraphic pile. So let's explore the consequences of thrusting a wedge-shaped stratigraphic package. So here we've got some templates before any thrusting. We have a horizontal layer cake, which is the conventional setup when you look at textbook examples of thrust belts. We can do a same sort of template but tilt it, so a tilted layer cake stratigraphy in the middle diagram, and then the bottom one we've got a wedge-shaped stratigraphic panel. The horizontal layer cake model creates an anticline in the hanging wall, but when you go behind that anticline, the top of the layer cake has returned to its original elevation. It's just moved in sideways. The tilted layer cake creates a structure like this, and the wedge of strata does something different. It creates a structure like this. So let's just analyze the vertical motions on here by constructing the regional, in other words, the regional elevation and orientation of a stratigraphic marker. We'll just pick the top of the green. So these are regionals on the top of the green layer. You'll notice that for the top diagram in there, It's only the frontal anticline that has uplifted the green rocks above their regional. As we mentioned earlier, as you go to the right there, behind the anticline, the green strata have remained at their regional. They just moved sideways in from the right. The tilted layer cake actually keeps those rocks below their regional as you go to the right. It's only thrusting the wedge stratigraphic section that has systematically moved all of the green rocks above their regional. So this is a great way of creating a plateau with displacements only really being accommodated by a thrust at the front. We don't need to thicken the stratigraphic pile to create the uplift. It was originally thick and it's just simply been moved up this inclined basal detachment surface. So plateau uplift is almost an unavoidable consequence of thrusting a wedge-shaped stratigraphic package, and we know the stratigraphic package was originally wedge-shaped by measuring the stratigraphic thicknesses from the foreland within the thrust belt and comparing those with as we see them on the Drac Valley in the hinterland. So the action really is confined to the frontal structures seen here on the margins of the Royan Basin. This is the mountain front, and you can see the elevated plateau of Vergonian rocks that lies to the right, forming those spectacular cliffs at Presles. So there's our cross-section. But there's still significant uncertainty into what these thrust structures do, particularly around the front. Do they simply pass down to the basal detachment? What are the displacements and the relative importance of the thrust that we've seen on this cross-section? How can we test models like this? Well, we're going to test cross-sections and their implications by looking at the implied lateral displacement gradients between the displacements we see on the cross-sections and the tips of the thrusts. And the Royan district is a really great place to do this. We're looking onto a Google Earth image here from the southwest corner of the boxed area on the map, and I've traced out on here the surface expression of two thrusts. One coming in from the top of the satellite image, coming in from the north, dying out towards the viewer at a tip represented by that circle. That thrust seems to die out southwards, whereas the thrust that carries the anticline that lies to the left, which on the map you'll see is called the Beauregard-Barré anticline, dies out to the north. So we have a Vercors front, and the thrust that carries that dies out southwards, and the Beauregard-Barré anticline and its thrust dies out northwards. And the Royan Basin lies between them, essentially rather like a relay ramp. So we're going to compare the section we've been looking at that I've drawn, so that's the Butler cross section, with a competing interpretation for the structural geometry of these thrusts published by Deville and Sassy. And that section lies a little bit further along from the one we've been looking at already. Let's look at the Deville and Sassy section. Here we go. On this section, they've not broken out the Ergonian as a separate unit. The Cretaceous is all shown as green. And what this section shows is the Beauregard-Barré anticline, BB, separated from the Vercors front. Now, this cross-section can be restored. So let's just briefly compare the equivalent section on my own version here, which was drawn along strike. So we don't expect the structures to match exactly. But there's some similarities. So what we're going to do is compare the displacements between these two cross sections. So here's the displacements on the Deville and Sassy, represented by heave for the Beauregard-Barré thrust there, picked out by the offsets of the Upper Jurassic. So the horizontal separation there between the two red lines gives the heave on that thrust, and we can make an equivalent measurement for the Vercors frontal thrust shown there. And you can see straight away the Vercors frontal thrust, according to Deville and Sassy, has got about a 4 times more displacement than the Beauregard-Barré thrust. For the Butler cross section, we can do the same thing. So we can measure the Beauregard-Barré thrust, which is the left end of the structures, and in this cross section, the Vercors frontal thrust breaks into 2 segments. So we'll have 2 thrusts that represent the Vercors front on the Butler section that is represented by 1 single displacement in the Deville and Sassy section. Okay, so these are the measurements we're going to make for displacement. Right, so here's our image again and the reliance of section. So these thrusts terminate laterally at tips. So at the tips, by definition, there's zero thrust displacement. And what we're going to do is compare the measurements of displacements we can measure from the cross sections with the proximity of the cross section to the relevant tip. So these are the measurements for distance to tips for the two cross sections. We might expect a systematic smooth decay in the slip towards each tip, and maybe the gradient should be the same for both thrusts. So let's see how this works out, shall we? So here we have a plot, displacement up the y-axis and the lateral distance along the x-axis. It's plotted north on the left, south on the right. So the plot terminates against the Beauregard-Barré tip on the left and the Vercors frontal tip on the right. So let's plot the data from the de Ville-Sassy cross-section. Here we go, here's their data. Let's unpack this a little bit. So the red bar represents the total displacement on their cross-section. In other words, the aggregate of the Beauregard-Barré thrust and the Vercors frontal thrust. So what's that? That's a total displacement of about, 8 kilometers. And it breaks into two segments. There's a Beauregard-Barré component there and a Vercors front component there. So if we put those two together, we get the total displacement. Now what we can do is measure the displacement gradient on each of these thrusts to their own tips. Here they go. The green line shows the decay in displacement from the section line of de Ville-Sassy towards the Beauregard-Barré tip, and a similar blue line showing the displacement dying away towards the Vercors front tip. And the slope of these lines gives the rate of change of displacement, in other words, displacement gradient, as you move along strike. Okay, now let's do the same thing for the Butler cross-section. This cross-section aggregates to show rather less displacement, something like about 6 kilometers, and again that's made up of a component on the Beauregard-Barré thrust and a component on those two segments of the Vercors front thrust. In this particular case, the Beauregard-Barré thrust on Butler's cross-section has a greater displacement than the combined two segments on the Vercors frontal thrust. So there is the gradient on the Beauregard-Barré thrust towards its tip, and it's interesting that it actually lines up exactly with the same gradients as the de Ville-Sassy. So our two cross-sections are compatible with one another. There's a smooth decay in displacement between the cross-section lines on the Beauregard-Barré thrust as it approaches its tip. But what about the Vercors front? The Vercors front gradient for my cross-section is broadly similar for that for the Beauregard-Barré. Those are more or less the same gradients, but is significantly less than the de Ville-Sassy gradient. For the Butler cross-section, the Beauregard-Barré thrust and the Vercors frontal structures show rather similar decays in displacement laterally. For the de Ville-Sassy section, the Beauregard-Barré thrust decays in displacement at one particular rate, but the Vercors thrust front decays really rapidly towards the south. So which of these interpretations would you prefer for the frontal structure of the Vercors plateau? Personally, I prefer my own cross-section because it implies a systematic change in displacement for both the Beauregard-Barré and the frontal Vercors structures that are the same. The de Ville-Sassy section, in contrast, has different displacement gradients for the different thrusts, which implies a non-systematic behaviour of thrust structures in the region. It's just a simple illustration of how we can use the three-dimensional structure of thrust systems, even if all we've got is a cross-section, provided we can link the cross-section to the tip positions of thrusts. And it relies on the assumption that thrust structures systematically change displacement as you approach their tip lines. So let's summarise what we found. We've seen that the thrust front of the Vercors plateau is located by a pre-existing normal fault, the presence of which we can infer by looking at the stratigraphic thickness variations between the foreland in the footwall side of the front compared to the stratigraphy exposed in the hanging wall. Other normal faults are chopped through and don't seem to reactivate or control thrust trajectories. The stratigraphic template is wedge-shaped, therefore moving up the gently inclined basal detachment generates plateau uplift. We don't need to infer a lot of internal thickening beneath the plateau, it's simply the original stratigraphic thickness variations being moved up this inclined detachment that generates the uplift. It's a really efficient way of generating a plateau. Finally, we examine the displacement distance relationships to thrust tips to make choices between competing interpretations of subsurface structure. So the Vercors area, a great area for understanding thrust belt evolution, the role of inherited structures and inherited stratigraphy in controlling the landscape and the structure. And because the frontal structures relay, we can use the proximity to tips to test interpretations of structural geometry as shown on cross sections.